Hello and welcome to Diplomatic Derivatives. In today's video, we're going to cover a new concept, which is involution. And also, we're going to see a theorem that is every group of even order has at least one involution. So we understand what an involution is and then move towards the theorem. But before going into the concept of involution, we need to understand two most important concepts in group theory, that is order of a group and order of an element. So what is order of a group and order of an element? First we understand this, then we understand what an involution is. So let's continue. So what is the order of a group? To say the least, the order of a group is the total number of elements in the group. That is, if G has 6 elements, the order of a group is 6. So this is how we represent the order of a group, by writing 2 lines and the alphabet of the group, that is the notation of the group in the center. So the order of G is 6 if the number of elements inside the group is 6. A very simple concept. But the next concept is, what is the order of an element? Now this is very important for understanding what involution is. We start with the order of an element. What is the order of an element? The order of an element is the smallest positive integer n such that a raised to n is equal to e. Now what does this mean? By understanding what an order of an element is basically the part of a group. So a group might have 6 elements, right? So each element will have its own order, okay? And what do we mean by that order? It's basically represented by this equation, which is a raised to n is equal to e, where a is an element of the group. So any element of the group that we take a. E is the identity element of the group. The operation could be addition or multiplication depending on the group. So either it could be a raised to n in case of multiplication, or if the operation which is assigned is addition to the group, then in that sense a plus a will be equal to e. So either a into a will give us e, or a plus a will give us e. So we'll just understand this with the help of an example. Here we're going to understand the order of an element with the help of an example. The example that we're taking is the integers mod 6 under addition. This is the representation for a modular group. So we'll understand what a modular group is in detail in another video. Here we're just going to use it as an example. So try to get a basic understanding of what a modular group is. In such a group, when we say Z6, Z is obviously integers, and 6 represents that there are 6 elements in the group. So since it's integers, we start with 0, 1, 2, 3, 4, 5. So these are 6 elements. And then the next element, there is going to be a cycle. So basically, it's called a cyclic group. This modular group is a cyclic group. Now, how is it a cyclic group? In a modular group, what happens is that when we have elements till 5, what happens is the next element, which is 6, will be assigned to 0. Then 7 will be assigned to 1, 8, 9, 10, 11, and so on. So we have 13 will be assigned to 1, 12 will be assigned to 0. And that's how the cycle continues. So this is one example of a cyclic group, and that is the integers mod 6. Now we are going to understand the order of an element from this group. So first of all, we take one element from the group. Let's suppose we're taking 2. So a is equal to 2. And since we're talking about addition, what we're going to do is we keep adding 2 to itself, right? So when we had on the previous slide, when we saw that the equation for order of an element was a raised to n, which is equal to e. Right? A raised to n was equal to e. That's just a basic formula. It depends on the operation, okay, which is assigned. So here addition is assigned. In case it's multiplication, we take the element and keep multiplying the element with itself to get the identity element, right? Here for addition, we keep adding the element to itself to get the identity element. So the number of times we do this process is the order of the element, okay? We'll just try to understand it by performing it now. So we take 2 mod 6. When we perform the operation of, when we are performing addition, and since it's a mod group, so we keep writing mod 6, okay, since it's mod 6 group. So first 2 mod 6 is 2 itself, because 2 is in the group. When we take 2 and add 2 to itself, it becomes 2 plus 2 is equal to 4. Now apply mod 6 to 4, you get 4 itself. Why? Because 4 is still part of the group. But when you add 2 plus 2 plus 2 3 times, when you do this process of adding 3 times, you get 6. 6 and apply, since it's a mod group, you have to take mod 6, right? So 6 mod 6 will give us 0. How is it giving us 0? Because in the set, it's in the group itself, you see after 5 we have 6, and 6 will be assigned to the first element, which is 0, right? So 6 mod 6 will become 0. So now here we get the identity element, because for identity element for addition is 0. So how many times have we done this process? We did it 3 times, right? So the order of 2 in Z6 is 3. Got it? So this is how we are performing the process of getting the order of an element. It depends on the operation which is assigned to us. We take another element. Let's suppose we take 3. So 3 plus 3 plus 3 will give us 9 if we do it 3 times, right? So apply mod 6 to it, because it's a 6 integers mod 6 group. If it's integers mod 3, you will take mod 3. If it's integers mod 4, you take mod 4. Okay, so it's mod 6. 9 mod 6 will give us 3, because 5, 6, 7, 8, 9. So we get 9 at 3. Therefore, 9 mod 6 is 3. But if we just do 3 plus 3 is equal to 6 mod 6, we get 0. So the order of 3 is 2, because adding 3 only 2 times will give us the identity element. So this is the order of 3, which is 2. Therefore, the order of 2 is 3, the order of 3 is 2, and that's how you will check for the rest of the elements as well. Okay, so this is the basic concept of order of an element. Now, if this is clear, we will try to move to the next topic, which is involution. So the next concept, the most important concept for this video, is involution. What is an involution? In group theory, an involution is an element that is its own inverse. That is, x squared is equal to e. Now, this is the basic equation for involution. When we say x squared is equal to e, we mean that x is one element from a group. Okay, and when we take a square of that element, for example, you multiply that element with itself, okay, we get the identity element. We don't have to do it 3 times, 4 times. That's not the case. We just take the element, multiply it with itself, and we get the identity element. So therefore, that element, and why are we saying that that element is the inverse of itself? Because of this, we have the fourth group axiom, which is the presence of an inverse, right? We have 4: closure, associativity, closure, associativity, identity, and inverse. The fourth one is inverse, and in that we say that A into A inverse is E. That is, you take an element, you take the inverse of that element, perform the operation on it, and you will get the identity element, right? So when we say that x squared is equal to e, and involution is an element that is its own inverse, it means that A is equal to A inverse, right? Because A is its own inverse, okay? And when you multiply them together, or whatever the operation is, depending on the operation, when you perform the operation on it, you will get the identity element, okay? This is basically the meaning of an involution, that it is its own inverse, okay? So if you say 2 ka inverse, the inverse of 2 is 1 by 2, right? It's not equal to it. 2 is not equal to its own inverse. But involution is something which is equal to its own inverse, okay? Because when you perform the operation on it, you get the identity element of that group. For example, we have 1 into 1 gives us 1. For a multiplication group, which is under the operation of multiplication, when you take 1 and you multiply it with 1 itself, that is, you are getting the answer as 1, which is the identity element of the group. So 1 is the identity element, and this basically tells us that identity element is always an involution. Okay, so apart from the identity element, there has to be another involution. Okay, so identity element is obviously, it's always true that it is its own inverse, right? Apart from that, any other element which is its own inverse gives us the under the operation will give us the identity element. For example, we take the mod group again, which in a similar way that we took integers mod 6, we will take integers mod 3 here. So 2 multiplied by 2 gives us 4, right? And 4 mod 3 is equal to 1. So Z3, the group Z3 is basically 3 elements, 0, 1, 2. And when you take 2 into 2, you get 4. Now, according to the group, you have 0, 1, 2, 3, 4. So 4 is assigned to 1. Therefore, 4 mod 3 will be 1. Okay, and 1 is the identity element of the group under the operation of multiplication. We are multiplying, right? We're not adding, we're multiplying. We get under the operation of multiplication, we get 1, and 1 is the identity element in the group under multiplication. Therefore, this is the involution. Okay, so 2 is an involution. Why is 2 an involution? Because you get the identity, when you perform the operation, you get the identity element. That is, when you are taking 2, you multiply it with itself. You're multiplying 2 with itself. You're multiplying 2 with its own inverse, which is itself. Okay, that's the basic concept. On to the theorem. So the theorem says every group of even order has at least one involution. When we studied what an order of a group is, order means the number of elements in the group, right? Now what we are saying is the group, every group which has an even order, so there's going to be either 2, 4, 6, 8 elements in the group and so on. So only even order, even number of elements in the group. That group will have at least one involution, at least one element that is its own inverse. Okay, that's a basic theorem. Now how are we going to prove it? Let the group have even order, that is G. Okay, so G has an even order. We're assuming that G is having an even order. So let the order of a group is equal to 2n. Why are we saying 2n? Because 2 with the number of elements multiplied, when you take the number of elements and multiply with 2, obviously we are going to have an even number, right? So the order of the group has to be even. So 2n represents the order of a group is even. So now the next step, define two sets A and B. We split the group into two parts. So we take the group G, and that group is splitting, we are splitting it into A and B. Okay, now what does A contain? A is equal to X element of G. X is an element of G, which is obviously in A because A is the set, right? Which is splitting from G. So X element of G, that is X square is equal to E. Now what is X square is equal to E? This is the representation of an involution. In the previous slides, we saw what is an involution. X square is equal to E. So that is the element which is its own inverse, when performed under the operation, will give us the identity element, right? So therefore this shows that in A we have only those elements that are involutions. Okay, all elements whose square is the identity, that is involutions and identity itself. So identity definitely is part of A, and also only those elements that are involutions, okay, they are part of A. Now what are the parts of B? Y is element of G such that Y square is not equal to E. Therefore, if they are not equal to E, means these are not involutions. So all those elements that are not equal to their own inverse, no involutions are part of B. All the rest of the elements are part of B. Okay, so what we are doing is we have a group G, we split it into two parts, we take A and B. A is only involutions and identity, and B is all those elements other than involutions. Okay, clear? Clearly, A union B is equal to G. That is, when you take A and B, make a union of those two sets, you will get G, obviously because you are splitting G into two parts, right? A intersection B is equal to empty set. That is because A is all involutions and identity, and B is everything else except involutions and identity. So when you take this, the intersection of those two sets, you are going to get an empty set. Every element is either in A or in B, not in both. So there is nothing common. Okay. So now comes the main part. We know that A union B is equal to G and A intersection B is empty set. First condition is, what if B is equal to empty set? We take the first condition, we take B as empty. Okay, if B is empty, then all elements are in A, because we know that A union B is equal to G. If you cancel out B, then A will be equal to G, right? So every element, X element of G, satisfies X square is equal to A. Since we are eliminating B, therefore everything of A is in G, and since everything of A is in G, A was all involutions, so all involutions are in G. So G has only X square is equal to E. Okay, which means every element is an involution or the identity. So G definitely contains at least one involution. So if we are taking this condition that B is empty, so therefore everything of A is in G, and G will definitely have one involution. Okay, this is the first part. Second, if we take B is not equal to empty set, means there is something in B. Okay, so B is not empty, there is something in B. We are assuming that there are some elements in B, that is elements that are not their own inverses. So they're not their own inverse. They have a different inverse. For example, 2 and the inverse of 2 is 1 by 2, right? So both of them are in part of the set. Therefore, it's a group, right? So we have those elements that are not their own inverses. Take one such element, y is element of b, then since y square is not equal to e, means it's not an involution, we know that y is not equal to y inverse. What is an involution? Involution means that y is equal to y inverse. That is, y is its own inverse, right? Which will under the operation give us identity. And since y square is not equal to e, we know that y is not equal to y inverse. So since y is in b and y inverse is not equal to y, so the two conditions, y is in b and y inverse is not equal to y, also y inverse square is not equal to e. It also lies in b. So since we are saying that y is not equal to y inverse, right? So when y has an inverse which is not equal to itself, and also y inverse will have its own inverse which is not equal to y inverse, okay? Therefore, for both, for y also the square is not equal to e, and for y inverse also the square is not equal to e. They are not involutions and they are both part of b. Therefore, for every element y element of b, its inverse y inverse is also in b and different from y. Okay, so it's very basic concept, just a little bit complicated, but once you get a hang of it, it's not complicated at all. We have y and we have y inverse. They are not equal to each other. Okay, they are inside b. Why are they not equal? Because we have already said that b is the set which is not having any involutions. Okay, therefore y is not equal to its inverse. So if y has an inverse which is not equal to itself, then y inverse has an inverse which is y, and they are again not equal to itself, right? So y square is not equal to e, therefore y inverse square is also not equal to e, and all of these lie inside b, okay, because they are not involutions. All right, this means the elements in b can be paired up as y inverse. So you can actually make a pair, means for example if you have 2, the inverse of 2 is 1 by 2 and they are both inside a set, so the pair is 2 and 1 by 2. So an element and its inverse, they can be made a pair. Okay, so similarly y and y inverse can be made up a pair. So when you have a pair, how many elements do you have in a pair? You have 2 elements, which is even. Okay, so the number of elements in B is even. That's what we're trying to prove, that up till now what we're proving is that B is having even number of elements. Why? Because since y is not equal to y inverse, y also lies inside B, y inverse also lies inside B. So when we pair them up, we have 2 elements inside the pair. Obviously pair is 2 elements. This proves that the number of elements in B is even. Okay, so if you have one element in B that is y and B is not involutions, there is also a y inverse. All right, so the elements become 2. Minimum 2 will be there. Okay, now the next part of the theorem is total group order. So what we are saying is, we know that the order of G is equal to the order of A plus order of B, which is equal to 2n. In the beginning, we proved that order of G is equal to 2n because it is even order, which is given to us. Since we are splitting it into 2 parts, A and B, so when you take the order of A and order of B, you add them up, you also need to get the order of G, which is even, right? Now we know that order of G is even, and now we proved that order of B is also even, right? Therefore, the order of A also has to be even, because if this is even, and there's an addition involved, obviously this also has to be even. It cannot be odd, right? Therefore, A is also even. But we also know the identity element, E element of A. We know that the identity element is inside A, right? In the beginning, that's what we talked about in the very beginning of the theorem, that identity element and involutions are part of A. Also, A is not equal to empty set. Why? Because since E is part of A, it is not empty. Since A is even, now here when we said that A, it has to be even because the other two are even and contains at least one element, that is the identity, then it must have at least one more element, okay? At least 2 elements in A. Why? Why does it need to have at least one more element? Because we say that it is even, right? We know E is part of A and we know A is even. And if it's even, there has to be at least minimum 2 elements. It has E, therefore there has to be another element, right? And we know that A is the set of all involutions only. Therefore, what do we have inside A? The next element. That element is an involution. Okay, so there must be some element x not equal to E such that x square is equal to E. Such that x square equal to E means such that it is an involution. Okay, so we have another element in A that is x not equal to E, that is not the identity element, and that element is an involution. Why is it an involution? Because in the beginning we assumed that A is a set of all involutions. Alright, so since there is an involution inside A, and finally we know that everything, we are splitting G into A plus B, right? So when something is in A, it will definitely be in G as well. Okay, so that's the major theorem. It basically is every group of even order has at least one involution. Now just to summarize this entire thing, because it might sound confusing, A is involutions only, okay, B is no involutions, G order is even, right? This is what we assumed. G is even, the order of G is even, B is no involutions, A is involutions only. A and B are the split up of G. We proved that B's order is also even, right? So order of A has to be even according to this, right? Since we know E is in A, as E is an involution, since we proved that, we already know that A will, since A is all involution, therefore E is in A. So there, to make the order even, there has to be another element in A as well, which is not E, other than E. There has to be, because we proved that A is even, right? Therefore, since E is there, there has to be another element as well. And since A is involutions only, therefore every group of even order has at least one involution. Okay, I hope I tried to make it as clear as possible. I hope it's clear. This is a kind of a complicated theorem, but it's very important. And this is how we prove that every group of even order has at least one involution. Okay. So from the theorem, we gather certain key ideas. Any finite group of even order must have at least one involution. So what do we understand from this? Group elements pair with their inverses. So as we saw in the part of B, where B has no involutions, so there is an element y, and the inverse of y is not equal to itself, therefore the inverse is y inverse, so y is not equal to y inverse, but they will pair together, so that will make the group that will make the set as even. Okay, so what we saw, that y paired up with y inverse, so you can pair up the group elements with their inverses. Involutions are the elements that are their own inverse. So involutions, for example, if you have y, if you have x, so the inverse of x is x inverse. And when you multiply or you perform the operation which is assigned, if you perform the operation on those two elements, that is x and x inverse, you get the identity. This proves that they are both their inverses. Okay. Odd one out must be one of them. So as we saw in the case of A, the set of all involutions, we have the identity. Any element other than the identity inside the group was the odd one out, and that one was the involution. Okay, so these are the key ideas. All right, so that's it. It was a longer video, but the concepts are kind of complex, and they are the most important concepts in the group theory when you start with the basics. So thanks a lot, and if you like the video, kindly like, share and subscribe to my channel, and I'll see you in the next one. Bye bye.